Yeah, so this is, okay. Yeah, thanks again, Duncan, for the introduction. I will talk about not the motor drives part of it, but for the grid forming converters and the system controls aspect of it. And I'm at North Carolina State University, and I would like to acknowledge the contributions of my former PhD student, Emea Wall, who is also a visiting scholar and that currently works at NANFAS, who has contributed to a lot of the system controls work and also helped me put together some of the materials contained within this presentation. So first, where are we and what we do? So the FREEDM, we are part of an engineering research center called FREEDM at North Carolina State University, which has graduated about 2 years back from the NSF. So now we are independent, independently surviving. So the FREEDM stands for Future Renewable Electric Energy Delivery and Management Systems Center. So we have about 12 faculty and about 80 PhD students. And we cover the spectrum of chip to package to application in the areas of wide bandgap power electronics, electric transportation, renewable energy integration. Let me get my pointer out, and power systems. So here's where we are located, this Science Center building in the Centennial campus, where you can see on the rooftop, we have the 40 kilowatts of power. In the parking deck, we have 10 EV charging stations, our chargers. In the pad here, 250 kilowatt of battery. And they are all connected within this building where we have this 15 kV class 1 MVA laboratory where we are housed. So the relationship with the talk here is like a lot of the work evolved from the FREEDM power distribution system, which was how we were addressing the grand challenge problem from for the ERC program, proposing a solid state transformer based power distribution system that would be intelligent and will also be incorporated with fault isolation devices and connect DC and AC microgrids on the other end of this solid state transformer. So the distribution system would be made up of these various components. And the research was broad, utilizing power electronics and information technology. It should be suitable for plug and play of the microgrids, and then enable robust and automated power, energy, and fault management. So this was the beginning of our work into the systems controls aspect. So as Duncan was saying, my original background has been on electric machines and drives, and then I went into electric vehicle systems and then into systems. And then working with my colleagues at the FREEDM Center, I got more into the system controls aspects. There is, of course, a lot of similarity where it ties in between a motor drive inverter and then the grid type inverter, particularly in terms of the hardware, but and some levels of controls as well. So they're not too different insert from a very high level perspective. So the early works were contributed by FREEDM researchers, which includes the partner universities, like we also like part of UNIFI consortium now, Saraja INR and Marissa Crow from MSNT. And then in the systems controls area, which FREEDM needed a lot of work on, is where me and Dr. Rani Chakraborty and subsequently some of our graduate students, including Awal, has contributed to that. And on the protection side, we do get a lot of input from our power systems colleagues, Dr. Baran and Dr. Lapkaman. So I just put together a few references here, but these are very few of the papers and publications that came out of the program, and there are many others that we have worked on over the last 5-7 years, particularly on the systems controls aspect for the modernization of the power grid, integrating renewables into the system. So the overall work incorporates both hardware and controls, and they are very tightly integrated. And I'll show you some of the hardware capabilities that we have that can be offered as a test bed. for UNIFI researchers. So one of our current projects is the development of a 1 MVA solid-state transformer-based electric vehicle fast charging station. So on the left, a 500 kVA unit at 4.16 kV has been built in the lab and then integrated. So this is a grid-tied converter, and it is being designed as a grid-forming converter. Some add-ons need to be included in this, but this is one of the tests, one of the hardwares that we plan to utilize for testing some of the controllers. And on the right-hand side, you can see some our power electronics for a network system. So here we have 3 low voltage SSTs, single phase systems, connected to the 240 single phase grid. Here he has the battery storage units, and this is reconfigurable to include the transmission line network model here, which can be reconfigured to provide various short circuit ratios with which we can test controllers. And then it has also a private cyber network for SCADA and secondary and tertiary control. So some of the experimental work that I'll show later utilizes these type of hardware resources we have in the center. So the hardware and the controls need to be designed in a synergistic way. Although we started the hardware and the controls development, for example, for that 1 MVA electric fast charging station, pretty soon we started to realize that there are a strong coupling between the hardware and the controls, and they need to be designed synergistically. And we started to apply these co-design concepts to the best we can. So this work is inspired by the works of Mario Sanchez and Daniel Huber, who says like how the physical aspects of an actively controlled engineered system such that the passive and active properties interact synergistically for system-oriented performance. So in terms of the faults and protection for grid forming converters, so there is a unit of the hardware, the inverter, the IBR, right? So that needs to have its protection at the unit level. Then it interacts with the system, and then there is system level protection also. So for the unit level, it needs to work into the hardware protection, the shoot-through protections, the DID to limits. If it's an NPC type power converter is used, then cell voltage balancing, and then handling asymmetric phase loading. Those type of protection components has to be incorporated in the controller for the unit. Thermal throttling for device derating, those all has to come. When you look at the system side, we have to evaluate and understand the system through large signal and transient analysis, system level control for transient protection, stability, and then the protection coordination in an IBR dominated network. And the coupling, one aspect of the coupling is through this fault write-through. So there could be others, of course, but like in relation to this talk. So the fault write-through aspects would be like the transient overcurrent limiting of the hardware, the fault current contribution that would support the system, reactive power support, the PF response, negative sequence contribution. So those would be the elements of the fault write-through controls that couples the unit with the system. So let me start with the hardware example. So the key aspect of this hardware design is the startup algorithm. The hardware itself, let me just briefly tell you about it. So this is a 3-phase 1 MVA unit built in a modular fashion. It has 18 modules, and the single phase, each single phase module has an input front end full bridge configuration. This is an NPC configuration that makes the active front end. Then we have a DAB stage, dual active bridge stage, that also has an NPC full bridge on one side, and on the other side of the high frequency transformer is another full bridge. So on the input side, these are cascadedly connected in series in a 3-phase configuration. So the key aspect, as I mentioned, about the co-design here is to think of the controls on how to build up the medium voltage side, focusing from or starting from the low voltage side. So the low voltage DC bus, which is output parallel connected, and here you can connect other units such as renewable generation or energy storage. And if you have storage connected, that could provide the startup in case of a black start situation. So black start capability is an essential for grid forming inverters. And then you have to think how we can enable that through the control design. And this co-design element serves us to get away from many of the constraints on how typically the medium voltage bus is started in other typical configurations, where it starts from the medium voltage side, from the input side, and then builds up the medium voltage. That puts a lot of constraint on the controller in balancing the voltages in those medium voltage bus capacitors. So with that startup algorithm showing an experimental result here, like the pre-charging of the low voltage DC bus, then in sequence it goes into building up the medium voltage bus, and then how you can see how they are uniformly maintained through controls of the DAB stage from the medium voltage bus. And then when the low voltage bus regulation is initiated, they are all having the same medium voltage, even though you are not actively controlling it from the front end of the system, or there is no communication between the DFE units for maintaining the medium voltage bus at each module. And then another experimental result showing the loss of load response. So here, 135 kilowatt of load was lost all of a sudden to no load. And these transients of the low voltage bus and the medium voltage bus are part of the controller design. And you can see that the medium voltage buses across the 18 bus caps, only 2 are shown over here. So they're still maintained to be the same. So let me see if I can move this away. When we talk about faults and protection, we must understand the scenarios of weak grids and then the power flow constraints, right? So we all define the strength of the grids through the short circuit ratio, which is in terms of the impedance of the unit. So in our case, it would be the 1 MVA unit that we're building. And the Z equivalent, the grid impedance, is the combination of this resistance and impedance. So this is standard theory that the power flow is constrained by the physical system, by the grid impedance. But when you look at the reactive power flow and analyze the system for different short circuit ratios, you will see that a minimum reactive power needs also to be maintained to achieve higher real power flow capability. So for this short circuit ratio 1 until 0.5 for this particular unit, we don't need any reactive power support, but to get some more real power flow capability, we must have some reactive power injection as well. So how it affects the inverter? Essentially, it affects the capacity of the inverter. So the key considerations here, okay, you can make these inverters large in terms of like incorporating those with large power devices with higher voltage and current ratings, but they all come at a cost. So what would be the minimum cost to build up this hardware unit with certain capacity so that it can meet certain power requirements for the system? So that is the question. One way of looking into or defining the high versus low penetration of IBRs, inverter-based resources, is through looking into the interconnection strength. So if we look at this system where we have few inverter-based resources beyond the left of this point of common coupling that serves some local loads, and we have a generator system here connected to this grid impedance, which could be the transmission line. So we can argue that like a weak interconnection where the short circuit ratio is high, seen from this point, which means that the grid impedance is high. Okay, it would make sense if we have enough generation and storage here to not, spend money on strengthening the interconnection strength here by putting more transmission capacity, because the local generation and storage should be able to meet the aggregate load demand. But if there is a high penetration of IBR, sorry, that was the case when there is a high penetration of IBR, so that would be in terms of weak interconnection, and you don't need to strengthen this grid. But if the penetration is low, that means the short circuit ratio is high. This generation source should be able to take care of any fault that would occur here, and then in that case, it may not be necessary to retain all of the grid forming converter capabilities for the IBR resources here. So now, with heavy penetration, the challenges are, these IBR resources could be heterogeneous type, various levels of inertia. They have different types of overload capacity and ride through capability and those things also. And then also for weak connection, the PLL becomes unstable. So this is a very, extensively studied, rigorously studied, and then we all know the issues when with high penetration and weak interconnection, the PLL would cause a problem. So the ride through in terms of the high versus low penetration, just to explain it a little more here. So looking from the inverter side, IBR resource side, if the short circuit ratio is large, means it's a strong interconnection. If there is a fault anywhere here, this unit, the generation, the synchronous generation can supply the fault current through this strong interconnection. But when the short circuit ratio is low, it's a weak interconnection, and the grid impedance is high, then this unit should be designed so that it can support the load currents locally as well as the fault current. And instead of increasing the strength of this interconnection by putting in more transmission capacity. So in the strong grid case, retaining the primary GFM response by the IBRs is not really essential. It can provide the terminal supported fault current contribution, and that would be enough. And if the interconnection strength is weak, then the common approach has been to switch to GFL operation under fault, and that would cause PLL issues, and that may destabilize the network. So retaining the primary GFM response under faults is of critical importance to maintain the feasible power flow, which means like to maintain the frequency and the voltage stability. So for the unit itself, in order of priority, what should be emphasized for its protection and controls is self-protection, being able to maintain the droop response, being able to contribute fault currents, and then also provide the terminal voltage support, and in terms of priority, which is in terms of its capacity as well. So the wish list that we have for fault write-through in the context of this is the IBR units must have transient overcurrent limiting. When there is a fault, maybe under normal operating conditions, there's an overcurrent limit, but under fault conditions, it may need to extend that limit by some percentage of the power unit to make sure that the IBR does not trip due to transient overcurrent at fault instant. And not only at the fault instant, this graph shows like when you're entering the fault current, fault mode, when you're entering the fault mode, oh, okay. The cursor is moving by itself. Anyway, when it's entering the fault mode, there will be an overcurrent depending on the operating condition. And again, there will be an operating point when overcurrent is possible when the inverter is coming out of that fault mode and going back into normal operation. So under both of these, the transient overcurrent trip should not occur for the IBR to keep continuing to provide support to the grid. And also the current limited primary GFM response, which are the power versus real power frequency and the reactive power and the voltage responses, should be retained under the constraints of the IBR's maximum current capacity. And all of the IBR resources here ideally should be able to, all of those that are GFM type inverters should be able to share equitably the real and reactive power loads, which would preferably be a byproduct of the primary GFM response. And note that when there is a fault, okay, so these units, in addition to supplying the regular load current, they must also support the fault current. And it's ideal if all of them, the resources can share in that fault current. And then the fault management algorithm should not be based on the fault detection method also, because we don't want any parameter changes or gain changes, so that we are seamlessly able to come out once the fault is cleared and then go back into normal operation. So the generic IBR controller would have this different levels starting from the lowest level of modulation, which is essentially topology specific, okay, and that's in the PWM time scale. And then there has to be the high frequency resonance damping for higher order filters like LCL filters. And that actually has an effect on the current controller bandwidth that can be achieved. So the next level would be current tracking, which is bandwidth limited, particularly could be due to these high frequency resonance damping requirements. The voltage tracking is not needed for the GFL converters, but needed for the GFM IBRs. And at the primary control layer would be the synchronization, the active power, and the DC side regulation, the reactive power regulation. The synchronization and power regulation are separate for the GFL converters, but they are merged actually for GFM converters. So where does the bandwidth limit for the current controller comes from? So we worked on a paper on a research on observer-based active damping, which we actually use in most of our controllers for of our inverters that are grid connected. And here, through an example, we show that like for this particular hardware topology, if we have a bandwidth of fs over 20, how the poles, would get into the unit circle from when the gain is the active damping gain is 0, it quickly enters into the unit circle, which means it would be stable. Whereas if we increase the bandwidth to go up to like fs over 8, the plot on the right shows that there is no stable operating point, as all of those are outside the unit circle. So faster and higher control bandwidth tends to result in the non-passive response in the high frequency range, where the digital control implementation, actually, there would always be inherently delays and then phase lag. And the damping of the high frequency resonances due to these higher order filters, limits the achievable effective current control bandwidth. And also the bandwidth falls with increasing grid impedance. So that's why we have a limit on the bandwidth that can be achieved for the current controller. And on top of that, of course, is the PWM frequency, and some inverters can also be frequency limited in the higher power and voltage ranges. So synchronization of the converter for the GFM converters and the GFL converters. Let me put this. So typically in the grid following converter, synchronization is achieved through phase lock loop, assuming that there is a stiff grid, but it suffers under weak grid condition. In essence, the PLL is based on PLL-based synchronization fundamentally is through the exchange of reactive power. Whereas grid forming converter, which relies on power synchronization, the synchronization is through the transient transfer of real power. So a weak grid condition is not so detrimental to synchronization for GFM converters, whereas it is for grid following converters. And also, of course, like for GFMs, the X over R ratio or the transmission line dynamics would limit the achievable synchronization speed. So grid following converters, I'll talk a little bit about some of the characteristic differences in terms of the different controllers for these two types. The grid following converters are current source nature, enabling fast current limiting response. And the transient stability is determined primarily by the power set points and the PLL dynamics. And when in a grid following converter, which has to do voltage tracking also, the expected voltage source nature of the GFN inverter actually contradicts with that current limiting response. And if you have to go into like a alternative method for fault under fault modes, then, for example, it could go into the current limited operation. The power synchronization process itself gets interrupted. So the synchronization process needs to adjust under fault, and that's why the simplest option has been to switch into a GFL type converter under faults. So what does that mean, limiting the current? There is a current limiter. So this is a GFL type control loop. The power synchronization block is shown here to generate the voltage reference. So the voltage controller feeds into the current controller. And in between, we have this current limiter to saturate the current reference. But if it goes into the limit, then it interrupts the power flow and affects the power synchronization block. So the synchronizing controller must be adjusted under fault, and a proper coordination is required between this power synchronization controller and this current controller under the fault mode. And ideally, what we would like is that fault mode algorithm is achieved without any parameter updates or gain changes or retuning of the controller, such that it is only applicable during the fault mode and not during the regular operation mode. So how would a fault right through strategy look like in a grid forming controller? So we have the power generation, power synchronization source. Typically, all fault right through strategies would look similar, where there is a dependent voltage source in series with the power synchronization block, which interacts with the current limiting mode using some feedback or some other variables in a feed-forward fashion. Also, it could be. And typically, the works that has been done so far is conceptually, this is how all fault right through strategies would look like. The nonlinear element inserted in series with the GFM or power synchronization controller. So it's possible that the nonlinear element could be part of this power synchronization controller. So that also could be done. But inherently, this nonlinear element adds dynamics. Okay. So ideally, what we want the fault right through response should be predictable and repeatable, which is a challenge from the analysis perspective and the system operator perspective, right? Because of the changing scenarios in the grid. So one method is to go into a double synchronous reference frame and utilizing a positive sequence and a negative sequence component. So the positive sequence component would be working for the power synchronization control, whereas the negative sequence would only be used for the synchronization control. So it should retain the PF group response in the positive sequence, and the reactive load can be shared by both the positive and the negative sequence components. And the reactive current regulation for fault current contribution and our terminal voltage support, and also for unbalanced mitigation, both the positive sequence and the negative sequence components could be utilized. So the distribution of the current capacity into positive and negative sequences is needed while ensuring the maximum capacity utilization of the inverter, not exceeding its absolute overcurrent limits, and also without affecting synchronization and or load sharing. So this is ideally what we would want. So I'm not going into the details, but like when we break it up into positive and the negative sequence, since the positive sequence limits are shown by this blue circle, so it has to have a larger component because it has to support the real power component as well. The negative sequence is smaller, and the net current trajectory is the combination of the two, which takes this form of elliptical. So from the inverter capacity limit, this constraint has to be maintained, that the absolute maximum limits of the inverter is within those elliptical characteristics shown here. So another thing is the analysis, large signal analysis, both under symmetric conditions as well as under asymmetric conditions. So we realize that there is a strong coupling between the angle dynamics and the voltage dynamics under the current constrained operation, because the current constraint comes from the capacity limit of the IBR. So these are the equations, but also traditionally what was done was separate analysis of the angle dynamics and the voltage dynamics, but this does not give you the full system dynamics picture. So we have been working on some virtual oscillator control methods, and others have done a lot more work prior to us, also a lot. So the VOC-based methods and the power synchronization-based methods exhibit first order power angle dynamics, simultaneously analyzes the V delta and the del and the angle dynamics, whereas droop and virtual synchronous machines exhibit second order power angle dynamics, which makes it more challenging because of the order of the system increases farther. So I'm showing you an example from our paper in this transient stability assessment noted here at the bottom. So just to quickly go over it, so taking into account both the voltage dynamics and the current dynamics in this left figure, prior to the fault, there's two intersections, and one of them is a stable operating point and the other is an unstable. And then when it enters the fault mode, you see there is no point of intersection. So actually, this is one of the scenarios presented both through simulation and experiments, where under fault, it enters the limit cycle mode. But through this assessment, plotting this in a 2D fashion, we can show that under fault, wherever from wherever you start returning from the fault mode to the regular mode, it goes into this stable operating mode, even though you are in this limit cycle scenario. So once you enter the fault and then the fault is cleared, it's able to come back to this stable situation. So the key message from here is the first order power angle dynamics is not limited by the critical clearing angle constraints, which it is, where the controllers are based on controllers are with second order power angle dynamics. So for large signal analysis, a symmetric condition, then now you have to deal with both the positive sequence and the negative sequence if we are basing our fault controllers on this double synchronous reference frame. So even with the first order dynamics, then you have 4 variables and the analysis becomes challenging. So these are open questions. How do we analyze it? Maybe the dynamic phasors or the generous DQ. Modeling could be candidates for symmetric dynamics, and it's even more difficult, as I mentioned, with the second order power angle dynamics. So next few slides, I'll quickly go over some of the examples of the fault right-through controller work that we have done. The details of those are in the paper, so I will not go into any of the details, and I'll just list the papers in here. And by no means like this is done. This is only the beginning, and there are a lot more challenging things ahead, and there are a lot more problems to be solved. So in this unified virtual oscillator control for grid forming and grid forming converters, the key aspect of it is there is no PLL and or backup controller required under fault. So this is PLL-less controller, and introduced a circular current limiter for current constrained operation under fault, and a fault has been simulated at the point of common coupling. And the hardware system is one of the test beds I showed earlier, has been used to validate the default right-through controllers using this hardware actually this would be in a 3-phase system also. We have implemented these controllers, and this gives you the ratings of the converter that we are analyzing. So some of the results here for symmetric fault conditions, 2 results are shown here when we have a weak grid type condition with short circuit ratio of 2 and then short circuit ratio of 10. In both cases, you can see that the voltage level is maintained at 0.6 per unit for short circuit ratio of 10 and all the way up to 0.94 at the point of coupling for a short circuit ratio of 2. But it is able to withstand the fault and ride through it and then come back to the normal operation. Maintaining within the maximum limit of the the converter capacity. So this IM is the limit, and then it has not been exceeded. Then the double synchronous reference frame has been used for riding through asymmetric faults. So here again, like we have a double synchronous vector limiter that goes into this space vector oscillator and then generates the positive sequence and the negative sequence commands for the converter. A fault simulated over here. Again, the key feature is no PLL is required under fault. And it enables flexible control objectives such as fault current contribution in both sequences, constant real power and reactive power, balanced current injection. So maybe it would be easier to show the results of how they're achieving it. And again, the hardware platform, it's a 3.3 kVA system, and three-phase voltage source ratings are given over here, which we experimentally used. And for the grid, we have used a grid emulator here to supply the to serve as the source, because otherwise, you know, it's very difficult to emulate the faults, especially like double line to ground faults and the three-phase faults. So the results here, so the key features are here. Once it enters the fault mode, both the positive and the negative sequence components are injected. And here it shows the negative sequence is 0, and then how it picks up once it enters the fault mode. So the VSC, one important aspect of this controller is to improve the unbalanced ratio. So with the injection of the negative sequence components, we are able to minimize the unbalance factor, which is the ratio of the negative sequence component over the positive sequence component. And it's shown here for both the single line to ground and the double line to ground. So again, I'm running out of time, so I'll very quickly go over these results of the three-phase faults. Again, what is shown here, it's being able to ride through and then limiting the current within the maximum current capacity for the IBR. And then again, two conditions of two different short circuit ratios are shown over here. So ideally what we want, as we are trying, those who are working on this fault ride-through controllers, how do we go towards the ideal, fault ride-through controller for GFM type IBR resources? As I mentioned, transient overcurrent limiting is important, and it could be a combination of feedback and feed forward for fast current limiting. Must be designed together with the high frequency resonance damping controller, and special controller hardware may be required in switching frequency constrained applications. Current limited primary response, the GFM response, and the fault load current sharing, as I had mentioned earlier, need to be maintained. But should at least, it seems like we should at least know some knowledge of the network, X over R ratios. So fault current and load sharing would preferably be a byproduct of the primary response. And as I mentioned, no fault detection based control algorithm adjustment. So by no means this is a comprehensive list. There could be many other components, but again, I try to highlight some of the important aspects of a fault ride-through controller. So that was the last slide. We have questions.